So in this talk, I'll present Comet. Comet is a neural framework for building machine translation metrics. And within this framework, we also released newer metrics that have been adopted by the MT community as a new way to evaluate systems. So this is going to be the main focus of this talk. Before we start, I would like you to introduce the usual. This is the Unbabel translation pipeline, but I'm pretty sure that this is common to most MT providers. So you receive an order, you just anonymize it, you pass it through your machine translation system. And then at Unbabel, we use a quality estimation system, which basically tells, by looking at the initial text and the translation that the MT gave, it tries to decide if the MT is good enough to send to the client. And if it's not good enough, we have a translator community that fixes those MTs. So they post-edit the MT. And then we just delivered the finished order. And periodically, we also have annotations that are made by experts, expert linguists. They do MQM annotations, and we use that MQM to check the quality of our delivered translations. So basically, these annotations are signals that we can use to integrate or to improve the quality of both our translation quality estimation systems, but also our MT systems. And the best way to do it is to, since we only annotate a few samples, the best way to do it is to try to train a metric that predicts those annotations and then use it during model development to evaluate our systems. We could also do annotations over all the systems that we have, but that would be super expensive, especially when we are just developing a new system. So Comet is going to be a proxy to this quality annotation. And why automatic metrics and automatic MT evaluation is important at the level. First of all, just a little bit more broad than that. Evaluation metrics shape the direction of MT research. We use them to compare experiments. We use them to decide what gets published. And we use them to also identify possible weaknesses and what we want to work on. And especially in a company, we need to use metrics to decide what gets deployed. But the problem is that this is a very hard problem, because we usually use metrics. Our metrics use a reference, so we take the translation and we compare it with the human translation. So if our algorithm is producing something that is similar to the human translation, we just say that this is a good translation. But as we know, we can translate things in many different ways. So having just one reference and just comparing to that reference, it's not enough. At the same time, it's very costly to be always creating these new references and curating references, because a lot of times we have parallel corpora, but the reference, it's not guaranteed that it's very high quality, and creating high quality references can be very expensive. And basically within Unbabel, we want to know if I have an engine A and an engine B, and let's say that the engine A is the engine that I have in production and I just developed a new engine. I want to know how I can, which one is better. And for that, our engineers were relying on existing metrics like BLA and Meteor. And at the same time, we were periodically doing MQM annotations, but this doesn't, if we just use metrics, they don't correlate that well. And if we just use humans, it's too expensive. So we needed to create something in between. I already talked twice about MQM and our annotations, quality annotations, but just to show you what I mean, MQM annotations, MQM, it's like a framework where you have like the entire context, and you have the original messages and the translated ones. and you want your annotator to mark on the text where he thinks there is an error, and then he has to assign a category to that error. And on top of that category, he also has to assign severity. So if it's minor error, major error, or critical error. So this is very fine-grained. And then we just take that score and we convert it. We just take these annotation spans and we convert it to a score using a formula that gives more weight to the criticals than it gives to the minors, and majors is something in between. But yeah, so just for your, from now on, every time I talk about MQM, is this type of annotations where they select errors and they assign, especially the most important part is the severity. And it's usually performed by experts, so it's very expensive type of annotation. So on one hand, we have human annotation, which is very reliable. It's made by experts, but at the same time, it's very slow and expensive. On the other hand, we had metrics like blood that are very quick. They cost nothing for you to run. On the other hand, they are not reliable, and they don't cover all the meanings that a possible translation can have. So the desire rate for automatic metrics, they have to have high levels of correlations with human annotations. This is the first. Otherwise, they are measuring something that it's different from what we care about. And this was possibly the point where most metrics were struggling with. They have to be sensible. So if you have small differences on your MTs, the metrics should capture that. They have to be consistent. They have to be reliable. So they have to be general, not gameable, and fast and lightweight. So far, we focused. So this is more or less on importance order for at least for the use case of Unbabel. Because like the not gameable is very important for research, because people can, if they learn how to tune the metric to get higher scores, they can just start publishing things saying that I have better results than you. But like for in a company setup, if we do the evaluation setting proper, this is not so important. The fast and lightweight, this is, we at first we didn't care so much about this because we always thought, okay, but human evaluation is always very slow, so let's not focus about being fast. Actually, this is something that we started working on because it's something that afterwards we realize it's very important. Most people were using BLA. BLA, I'm not sure if you are familiar, but BLA basically measures the n-gram precision for between an MT translation and its reference. So, and BLA is very much like, it's 100% lexical. It doesn't take into account like differences that can have the same meaning. And that's why that's what Meteor was trying to solve. So Meteor already uses includes some semantic equivalents like inflections, synonyms, paraphrases. So it includes a little bit more information about semantics and not so much lexical information. And Meteor was much better than BLA was, but still, it's still very far from what we desire. Ideally, what we want is to have an algorithm that, given an hypothesis, you can pass a reference, but that algorithm will compare the hypothesis with, for instance, the source and the reference, and it will compare it in a semantic way. So paraphrases, if they are correct, if they are fluent, they should have the same score, or somehow the same score. And most metrics were still not doing this. Okay, I'm just gonna skip this because I just say this. So that's why we proposed Comet. Comet, it's an abbreviation of cross-lingual optimized metric for evaluation of translation. And what Comet does is it relies on a big pre-trained model. It's XLM Roberta to create, it receives the source, the hypothesis, so the translation that you want to evaluate, and a reference. And it's basically going to use XLM Roberta, which is a big and large pre-trained model for more than 100 languages. And it's going to create a sentence embedding for source, hypothesis, and reference. And then we just combine those sentence embeddings in a way to that tells you how close is the hypothesis to the source or the reference. We combine them and we extract that information to a feed-forward that will produce a score. And this score over here can be, for instance, the MQM score. We can train, since we have annotations of MQM on the hypothesis, we can train this model to predict the hypothesis MQM here. So a little bit more about the details. This is the way that we do the embedding concatenation. So we get the embedding for the source, the embedding for the hypothesis, and the embedding for the reference. And we apply the element-wise dot product between hypothesis source, hypothesis reference, and we also apply the absolute difference between them. So when we do this, we are basically comparing feature by feature how close are the representations of the hypothesis compared to the source or the reference. And this is what we pass to the feed-forward that will produce a score. And it's optimized with mean square error. Now, what we sometimes, depending on the data sets, and I'll talk a little bit more about the data that we use to create these metrics, we can have data that basically, given a source and a reference, gives us a good translation and a bad translation. The bad translation, basically, I just said bad, but it's not bad. It's worse than the good one. So sometimes it's still a good translation, but it has some named entity that it was not well translated. So it doesn't mean that it's a completely wrong translation. But if we have this data where we have a good translation and a worse translation, we can just create the embeddings for the anchors, what we call the anchors, so the source and the reference. We can create the embedding for the positive hypothesis, for the negative one, and we can use the triplet margin loss, which will basically, in the embedding space, so in this semantic space, it will create a representation for the positive hypothesis that it's closer to the anchors than the negative one. And this was our translation ranking model. So these were the two models that we developed within the Comet framework. And then our work was mainly try to use these models to create a new metric that would correlate better with human judgments than previous ones. So this is more or less about the architecture. Also, just a few Comet specifics. When we create the sentence embeddings, we use average pooling. We also tried the CLS token. CLS token doesn't work so well, but the difference is it's not much. This is just a small boost that we receive by using average. This part I already told you. And we also use layer-wise. So one of the desires of the metrics is that it's very general. So it's very important for us not to overfit the data that we use for train, because we want metrics to be applied to several different domains. So we need to really care about generalization. And as a developer of a metric, I prefer to lose a few points in my dev set, but have something that I know it's general, than trying to hill climb the development data that I have and then have something that works very badly for other domains. So we also to try to avoid that, we used some tricks, some deep learning tricks like layer-wise learning rate decay, which basically takes for each layer of XLM Roberta, which has 25 layers, I believe, or 24, the learning rate is going to be smaller and smaller and smaller for the lower layers, which means that the first layers almost don't get any tuned. And we also do fine-tuned schedule, which means that we keep XLM Roberta frozen for a period of time. And then we only after that period of time, we start doing the fine-tuning. And the idea here is that the encoder already knows a lot of information. We want the upper layers, like the feed-forward layer, to learn something before we start blaming the entire model for the error. And on top of that, we also kept the embedding layer frozen. But yeah, these are just small tricks that are very important to create something that generalizes for several domains. Okay, so a little bit about the data that we used. At Unbabel, we use MQM, but the public benchmarks usually don't use MQM. They use something that it's called DAs. And a DA, it's basically, I have some example here of a DA, I think. Okay, maybe I don't. Okay, but a DA, it's basically, you ask an annotator to give a score between 0 and 100 of how good he thinks the DMT is. Right. So I was talking about the data. So there is different data that we can use. Internally, we use MQM. MQM, I already explained what it was, but public benchmarks don't usually have MQM data because it's more expensive. Only recently, we started having some public benchmarks with MQM annotations, but mostly people use HTER, which is Human Meditated Translation Edit Rate, and direct assessments. HTER, I have here an example of an HTER data. You have a source. That source gets translated by an empty system. And then you ask an editor to fix the translation by changing only what is required. So they cannot start paraphrasing the empty just because they don't like the words. They just have to focus on changing the minimum amount that they can to fix the translation. So after you have the source, you have the hypothesis, you get the post edit, and then you also have a reference that was a translation created directly from the source without any bias of the machine translation. And HTER is just the edit distance between the empty post edit and the hypothesis. So if this edit distance gives you, if the edit distance is high, so it means that the editor needed to fix a lot of things in the hypothesis. If the edit distance is very low, it means that the translation was already very good, so they didn't have to fix anything. So what we can do is to take the source, the hypothesis, and the reference, and we can train a Comet model that looks at these three things and tries to come up with the HTER score, which is a proxy of how good the translation is. So we have a lot of HTER data available. We can train a model based on HTER. We have, especially, we have this KT21 corpus, and we also have the ApeQuest corpus. Yeah, MQM data, we also have a lot of MQM data internally, not externally. Externally, we started only having this year because of the metrics share task, changed from DAs to MQM. But we could, when we started developing Comet, we could already use some internal data for it. So we also experimented with MQM data. So Google, we have the MQM data that we have available now. It's based on, it was annotated by Google. They use just a note that they use a slight different way to come up with MQM scores for each segment. But Unbabel, which follows the original proposal of MQM, whenever you want to create a segment level score, you apply this formula, which gives different weights for the different categories. And the major errors are multiplied by 5, criticals by 10. Google doesn't do that. They have a non-translation error that has a weight of 25. Then they have some minor errors. Most of them have a weight of 1, but some of them have a weight of 0.1, which is almost anything. And they don't have this idea of the critical error. So mostly whenever they find one very bad error, they just give this 25 weight. So the weight scheme is slightly different, but they more or less convey the same image of the quality of your systems. Every year for the WMT shared tasks, the organizers collect another type of human judgments, which is called direct assessments. And this was the part that I wanted to show in the last, in the other presentation. Direct assessments are these quality scores given by humans between 0 and 100. So here we have a source, a reference, and then we have, because on the WMT shared tasks, people submit several systems, they get several hypotheses, so several different translations for the same segment. And then they just ask humans to give a score between 0 and 100 of how good is this translation. What happens is that if you have several hypotheses for the same source and you have different scores, you can come up with a relative ranking. So you can say that this translation over here is better than the first translation, because the first translation was assigned the score of 0 and this one was assigned the score of 90. So you can come up with this, which fits perfectly into our translation ranking model. On the other hand, you still get these scores. So you can translate, you can use the DA scores for two things. You can use them to translate, to create a model that regresses on a score, like our estimator model, or you can use the rankings to create a translation ranking model, like our translation ranking model. Yeah. Okay, so this was the data that we used initially. So going back to this slide, we used HTER for regression, MQM for regression. We used internal MQM for this, and we used DAs for regression, but also for ranking. And in our first experiments, we just take those architectures that I had here. We train these architectures with the different types of assessments. And our goal was to understand how good, which type of assessment would produce the best metric and which architecture would produce the best metric. And this was our goal, initial goal. The evaluation setup that we used was based on WMT metrics share task, which is this competition that occurs every year about creating the best metric. And they use these relative rankings that I just explained. And the goal of a metric is to give a score to the better hypothesis and also give a score to the worse hypothesis. And the score of the better hypothesis needs to be higher than the score from the worse hypothesis. And the metric that they use to evaluate the quality of machine translation metrics is this formulation, which it's a Kendall-Tal-like correlation, which measures how much time your metric is going to agree with the human ranking versus other metrics, for instance. And here we can see the results. These are the results from our initial paper. So for German into English, you can see, for instance, that BLE, which is one of the most used metrics, doesn't have almost any correlation. This Kendall-Tal formula goes from -1 to 1. So having 0, it's basically randomly assigning which one is the better hypothesis. Having something close to 0, it's randomness. Then you also have CHRF, which is very much a lexical metric. It improves a little bit over BLA, but you can clearly see that there is a jump between lexical metrics and more semantic metrics like BERT score, BLERT, or PRISM. And then you also have the different models that we trained. So Comet regression model with MQM data, Comet with H-star data, Comet with DA data. All these three are regression models, and we also have a ranking model over here. So overall, it looks like that training on direct assessments, it's better than training on the other type of assessments. And it looks like that having the estimator model is better than having the ranking model. There is just some differences here that make this comparison a little bit unfair, which is we have much more data for direct assessments than we have for the other two assessments. And the Comet ranking model was very hard to scale for the large XLM Roberta, while the estimator model was working well with XLM large. So the number of parameters for this model are like twice the parameters of this model. And the data for this model is also twice the data that we used for these two models. Nonetheless, the data and the size of this model here, it's very comparable with the BERT score and BLERT, and it's even smaller than PRISM. Okay, so the results out of English were very positive. This is the segment level results. Sorry, this is into English. Out of English, it was even better. We had a bigger difference from state-of-the-art metrics like BERT score or PRISM. And this also works well whenever you don't have any English, so in the source or the reference. So, and we didn't have any training data for this, so this was completely zero shot, in the sense that we had some German data from English into German and German into English, but we never saw German into Czech or German into French. So after the initial paper, we participated on the WMT20, which is the competition that I was talking about. In this competition, we ended up winning most of the segment level language pairs. So similar to what we see here, our metric was one of the best performing metrics. Just the only difference that we did was that we were training with the data from 17 to 18 and testing on 19 because we didn't have any test set available a part of that. And for our submission, we just included the data from 2019 into the training, and we just submitted not blindly because we had a small set that we kept, but almost blindly to the shared task. Note that we still had a lot of work just trying not to overfit the metric. Okay, so this is going to be now the second. So this is all about the work that we did on Comet. Now I'm going to tell you just a little bit about MT Telescope. I'm not going to tell you much because we are going to have a tutorial that will keep talking about this new work that we did, but just the motivation about it. Like even with a very good metric, which is Comet, a lot of times our researchers were facing this decision where you have, on one hand, you have a system with 86.7 Comet points, and on the other hand, you have another system with 86.8. So it's very hard to just look at the score and tell that the second system is better than the first one. There is a lot of things that can influence this score. And our goal with MT Telescope was to try to have something that would tell us that indeed this system is better than this one, or at least that tell us that there is not a lot of difference between the two systems. Maybe it's not even worth to deploy the second system because you don't know how it's going to behave on out of domain. And at least this one it's very stable. So we wanted our researchers to have an easy way to answer this. And the MT telescope is just an easy to use web interface where you could go through several segments and look at the data, look at the differences between translations. Here you can see that you have a system X and a system Y. The difference between scores, it's 0.72. It's quite a big difference. And if you look at the translation of system X, you have here the word archangel, and this word should not have been translated. So in the reference, if you look, you have here another word that it's not archangel. So this was a wrong translation done by the system, and that was getting penalized a lot. You can also see more into the system level. You can also see the buckets plot where we try to group translations that we think are critical errors. We try to just group the translations that we think they just have minor errors. And we try to give you a comparison within each bucket between two systems. Because what happens is that sometimes we can have two systems with similar scores, but one of them is producing a lot more critical errors. And we want to be able to show that. Now, a little bit more about ongoing work. We had these architectures. In all of these architectures, we used the reference, but we also use the source. And ideally, the source, if the model that we are using to encode the text is highly multilingual and semantic, the source should convey all the meaning. So after we released Comet, we also started wondering if we could use just the source as a signal to evaluate machine translation. And it was not just us. We also, on the WMT metrics task, it was highlighted that the reference-free model from Comet, which we submitted, but we didn't test it a lot. We didn't make a lot of testings to that model at the time, but we just excluded the reference and trained the same model. And it turned out that that model behaved really well on the WMT metrics task. On top of that, another independent study from Microsoft, they just tested several metrics on a lot of enormous data that they collected over the past 2 years. And Comet and Comet source, which is the Comet without the reference, both these metrics were ranked the two highest performing metrics. And this was very surprising because Comet source, it was not intended to be competitive with reference-based source. So we asked the questions if references were really needed. This is the overall architecture of Comet QE. So we call it QE because within the field of machine translation, whenever you don't use the reference, it's called quality estimation. Whenever you use the reference, it's called a metric. But the difference between both, it's very small. It's just one input away. And this is the architecture. Also, as I told before, we wanted to not only create something that was independent of the reference, we also wanted to try to create something faster. So we replaced this XLM Roberta encoder by Mini LM V2, which is a model by Microsoft also. It's a very tiny model, but it's a distilled version of XLM Roberta, and it's much faster. So in our submission to the WMT21 share task, we tried to participate with a smaller model and a reference-free model. And on top of that, since last year, not last year, this year, Google released in the beginning of the year, they released MQM, publicly available MQM data. That data was used for the share task as development data for most metrics. We tried to take Comets trained on DAs and we tried to steer it towards higher correlations with MQM. And this was something that we never did before. Even though we were already using MQM, we never thought that we could take a metric that is trained on DAs and just try to fine tune it towards MQM. And turns out that this works very well. The only trick that you have to do is that you have to normalize the scores, the MQM scores, in order to be z-scores. And these z-scores are close to what we use to train DAs. So you just give one epoch of fine-tuning and you have a new model that is much more correlates much better with MQM. And so we did this Comet MQM model with and without a reference, and with a smaller encoder and also the large encoder. We did all those variations. On top of that, we also, since MQM has these annotation spans, we thought that we could train a tagging model, and we developed this on top of a great framework that it's called OpenQE. This framework was the intent of this framework is just quality estimation, but we decided to try to use it for MQM prediction. And we do this multitasking between MQM and word tags. And this works well because basically the model learns where you have errors in the translation by just looking at the source and the translation. And these were our results. So as I was saying, we have several versions, but if we look at the reference-free versions, the models that are reference-free are very competitive with the models that are reference-based. And on average, you have here, like the difference is just 1 point. And also OpenQE performs relatively well. And it's a tagging model, which it's also something that is surprising. Note yet that these results, since after that, the metrics organizers run another MQM annotations over new data, and the results are not as high, but the best metrics are still the best metrics. So the ranking between the metrics are still very similar. Okay, here are the official results. So you can see Comet MQM, which is the reference-based model. It won 10 different settings. You also have Comet QE, which won 3 of them, and OpenQE, which is on pair with Comet QE. But then you have all the metrics that are below are reference-based metrics. So all of these metrics are reference-based, and our 2 reference-free metrics are on the top of the leaderboard. And then you also have Comet with reference. You have CSPEC, which is a new metric. It's very similar to Comet, and BLERT, which also it's very similar to Comet. It's developed by Google. And these were the official results from this year. Okay, and this basically summarizes our participation to this year's share task. Now I'm just going to tell you a little bit about this new work that we proposed. We have seen that most of these metrics, like all of these metrics that we have seen in this plot, which not plot, this table from the official results of this year. First of all, the top 3 metrics are learnable metrics. So they are based on big transformer models, and they are very similar to Comet in that sense. And then all the below methods are more lexical, and some of them are also based on these pre-trained models like these 2, but others are not, like Lepore, it's very lexical. But on all of these metrics, especially the ones that are trained on top of big pre-trained models, they only provide you an estimate of the quality. It's just a single point that tells you this machine translation has a score of 0.8. But maybe we are interested in in having some confidence interval that tells me where my quality is. And if the model is very uncertain, that confidence interval should be higher. And if the model is very certain about the empty quality, that the confidence interval should be very small. I have here this plot. This is a true example where the ground truth direct assessment was minus 0.8 and Comet predicted 0.5. It's a very bad prediction from Comet. And we tried to estimate the confidence intervals, and turns out that the confidence interval almost every time contains the true direct assessment. The problem is just that the model is very uncertain. So the predictions are very off, and they have a very wide confidence interval. But if you get this, if you have a way to represent this distribution, maybe you can fix the score by applying the mean. So here is the fixed score. Or you could just throw away this segment because you don't know what is its quality. And here we see an example where Comet is doing a good job and the confidence interval is much more wider. So the methods that we use here are deep ensembles. Deep ensembles are basically, we train 5 different Comet versions with different seeds, and we use those to, we ensemble those to have our uncertainty aware Comet. And we also used Monte Carlo dropout, which is basically, you just turn, during inference, you turn the dropout layers on, and you just run several inferences. So deep ensembles are very costly to train, but they are not so costly to run after you get the models. Monte Carlo dropout is very costly to run after, although you only have to train the model once. And according to our experiments, as I was showing in this plot, if you use this uncertainty-aware Comet, your correlations with human judgments improve even more. And you can also try to use them to spot where Comet is not doing a good job, like a new domain that Comet is very uncertain. You can, in our paper, we also try to use this to detect critical translations. So if you are interested in this topic, I advise you to read the paper. It's the link is here. I can share the slides after. And yeah, that's it about our work on Comet, empty telescope, and these new works. One of them tries to get rid of references. The other one tries to measure uncertainty of these models. And I'm open to questions. So we have 10